In this part, we are going to discuss how to properly bias a transistor to make it an amplifier. As you may remember, in this curve, and this is the vertical axis is the collector current, and the horizontal axis is the collector emitter voltage. And this is the DC characteristics of the transistor. And this black line is the load line and we have. As you can see, we need to properly bias the transistor to an optimal point, somewhere in the middle. That will allow us to get a maximum swing voltage output. Now, if this point is not properly biased, for example, if it goes to somewhere either to the top or to the bottom, apparently our amplified signal will be cut off. However, it is not an easy job to properly bias the transistor, and there's many kind of reasons for that. The transistor might have a different and beta value, right? Even the same transistor, its beta value might be changed when the current is changing. There's many type of biasing configuration, and here is an example for bias the transistor using a single power supply. And with a single power supply, on the left figure, we can use a voltage divider and to generate a stable voltage that will drive the base and will generate a stable base current. Or we can directly use a resistor RB here, as long as we can properly choose this value, and we will be able to generate a stable driving current into the base. Now here's an example for using a voltage divider to bias the transistor. Now this voltage divider on the left side of this circuit can be further simplified based on the Thevenin equivalent analysis. As you may remember, in the Thevenin equivalent analysis, for this voltage divider, and the voltage output is here, so we call it open circuit voltage. That open circuit voltage can be calculated by this formula here. This is basically a voltage divider equation. So VBB equals VCC times R2 divided by R1 plus R2. Now this is the open circuit voltage. And we also needed to figure out the Thevenin equivalent resistance in order to get a simplified model. So the Thevenin equivalent resistance can be easily obtained by looking into the circuits from here. Now, when we do the Thevenin equivalent analysis, we need to ground any voltage source, which means this needs to be grounded, and this is grounded, apparently R1, R2 in parallel, and then we obtain the Thevenin equivalent resistance and equals R1 in parallel with R2. And now we have our voltage supply at here with VBB, and through a resistor it's IB here, and this is the equivalent circuits. And this will generate a stable RB and then the base current into the transistor. For this loop, we can apply a KVL. Now this KVL equation, from this KVL equation we can see this RB here, and we can replace this RB with the base current by the emitter current with this relationship we have before. And then we get this new equation here. And with this new equation, and we can rewrite, eventually get the emitter current. And this is after the biasing, this is the emitter current we should have. And in this emitter current equation, we want this current to be less sensitive to our beta value and our VBE value, right? We know this VBE is changing when we have a AC signal get into the base. So which means we need this VBB value should be much larger than this VBE here to make it less sensitive to this VBE. And also in order to make it less sensitive to this beta value, which means this RE here has to be much larger than the second term. The second term in the denominator is RB divided by beta plus 1. So to design In summary, to design a stable biasing circuit, and we need to have these two conditions to be satisfied. However, in reality, we always have some limitation on the VBB we can obtain, right? This VBB is from the voltage divider. And also this RB value here. We want this RB value as small as possible, but this RB value is small, then we are going to drain a lot of current from the voltage divider circuits. Usually, we can use the rule of thumb to design the biasing circuits. Now, here's the rule of thumb. We can design or make our VBB equals 1/3 of our VCC here. And also our VCE, which is the collector emitter voltage difference, will be also about 1/3 of the voltage supply, VCC. And we also want to make the voltage drop across this RC resistor to be 1/3 of this VCC. And we want the current through our voltage divider will be a little bit smaller than our emitter current. Usually, we can choose between the same value as the emitter current, or 10% of the emitter current. Now, this is some kind of rule of thumb to help us for our design. Now here, we can show you an example on how to make the design. So to design a circuit below for VCC equals 12 volts using the rule of thumb we just mentioned, to establish a current, emitter current equals 1 milliamps, and assume our transistor has a beta value of 100. Again, we can simplify the voltage divider circuits using the Thevenin equivalent analysis, and we get our VBB voltage here, and also our Thevenin equivalent resistance value RB equals R1 in parallel with R2. And with this analysis, and then we can figure out how to make the proper design. A rule of thumb is to make an VBB equals 1/3 of our VCC. Assume we can ignore the current into the base, because we know because beta number is about 100, and the base current is 100 times smaller than the emitter current. And if we use a rule of thumb to apply a 0.1 or 10% of the emitter current through this voltage divider, no, the base current is still much smaller than the voltage divider current. And if we ignore this base current, and we can easily get our VBB or VB voltage, that is about 4 volts. 1/3 of 12 gives us a 4. So the voltage at the emitter side, we can calculate. Now here we have on the base voltage is 4 volts, and the VBE we know typically is 0.7, and then we are able to get the emitter voltage at 3.3 volts. We have our emitter current equals 1 milliamps, and then we are able to calculate how much RE we need. RE will equal VE divided by RE, that is 3.3 volt divided by 1 milliamp, will give us 3.3 kilo ohm. For the RC value, using the rule of thumb, we need to 1/3 voltage drop across this RC. The 1/3 voltage drop, that is 4 volts. And 4 volts divided by 1 milliamps. And because the collector current will be almost the same as our emitter current, and we will get 4 kilo ohms for the RC here. Now let's figure out how much R1, R2 do we need. Since here we need a voltage at 4 volts, and then the VCC is 12, then we know the voltage difference, a voltage drop across R1 is going to be 8 volts, and the voltage drop across R2 will be 4 volts. And if we design our voltage divider current as 0.1 RE here, and then we will be able to calculate the resistance value of both R1 and R2. So R2 will be 40 kilo ohm and R1 will be 80 kilo ohm. Now let's plug in those values to the emitter current equation we just derived. And then we end up with a 0.93 milliamps, which actually is slightly different from the value we needed to design, that is 1 milliamps. Now in order to reduce this error, the one approach is we can probably try to increase the voltage divider current. But if we increase the voltage divider current, that will drain more power, right? So that's another disadvantage. Now here's another version of single power supply. Here, actually, we just put a RB here, directly connect between the collector and the base. If we apply a KVL from VCC through RC and then through RB and then EBJ here, and we will get this equation here. And from this equation, and again we replace this RB by our RE, and again we get the same thing as before. We can get the emitter current here. From this formula we can tell we still need this condition. This RC has to be much larger than this RB divided by beta plus 1, right? And also VCC needed to be much larger than our VBE here. From the example, we know that it's not so easy to properly bias the circuits, even though we have some design, but we end up with a different value. Now there's another way to bias the transistor, which is the current using a current source. And if we can have a stabilized current source, that will be a very good solution, right? But how can we get a very stable current source? Now this actually can be obtained through a current mirror. And on the right hand side of the figure is a current mirror circuit. Now these circuits will give us a stabilized current. Now let me show you why we can get a stabilized current. Now in this current mirror, and we have a two transistor here. Now these two transistors has to be matched. Means they have to have the same geometry or same parameter, especially the bit value. Usually they have to be fabricated at the same location at the same time. In this current mirror, so Q1 is called diode connected BJT. And if you look at the connection here, so the base is directly connected to the collector. Now once we have this kind of connection, then we are going to force the transistor either working at the active mode or working at the cutoff mode. There's no way we can get into the saturation, right? Because of this kind of a connection. If we have a reference resistor here, and since this is connected, we have a VBE here. VBE is almost a constant, right? Which means this is a constant value, and this will be some value of VBE. So the current through this resistor will roughly be a constant value. And if we apply a KVL from here, from VCC to negative VEE here, and we can write down the equation, this VCC equals I reference times this R, that gives us the voltage drop, and this is our VBE minus VE, right? If we write, and we can get this reference current. Because our two transistors are matched each other, and they have the same VBE here, right? Their VBE will be the same. So which means their current or base current will be the same. If they have the same current, and they are going to get the same collector current. So that means the collector current on Q2 in Q2 is also the same as the collector current in Q1. So that will give us the I will equals RF. So we can use this current to drive another transistor and to bias that transistor, right? So this is the That is a pretty good design for this current meter.